Newton Institute for Mathematical Sciences. I'm for the first time here, and so I'm very satisfied with the general climate, working climate at this institute. So thank you. So the title of my talk is on the negative spectrum on quantum graphs, and just a few words about the content of my talk. This is a short outline. First of all, it will be some kind of introduction. We will settle the notations and so on. This is the first part. And further, we will deal with a negative spectrum of Laplace operators on metric graphs. So one can ask why this question, why it is reasonable to deal with these questions. So there are different motivations. I will mention one motivation. So if one deal with semi-groups on metric graphs generated by differential operators, there are questions which are related to estimates on the negative part of the spectrum. It's also related to some questions on Brownian motion on metric graphs and so on. So I will not speak about those things. So that's a program for the talk. Okay, let's go further. First of all, let's settle the notations. So we have some finite graph, G. So it has vertices. The set of vertices will be denoted. It's red points on this plot. This set will be denoted by V. And some of these vertices are connected by edges. So we are, multiple edges are allowed. This means the edges which, so a couple of edges connecting the same two vertices. So we also allowed for loops, something like this. And besides the standard vertices which connect two, standard edges which connect two vertices, we will allow also presence of, so to say, non-compact edges, or we will call them external edges, so these blue lines, which has precisely one vertex as a boundary of this edge. And in the sequel, we will decompose the edge set E as the union of the set of internal edges. These are the normal edges, which has two boundaries in any case, and the blue edges, external edges. In any case, some of them may be empty, some of them may be absent, and we will suppose that the edge set is not empty. That's all. And just to mention, so we will always assume that the graph is connected. From one vertex, there is a path to an arbitrary other vertex. So, okay, next step. We will introduce the orientation of this graph. This means any edge will be considered as an oriented edge. So it's quite arbitrary. We need this to introduce the local coordinates on the graph. This is the same story as the introduction of local coordinates on, say, Riemannian manifolds. And for these things, we need orientation. We have to say what is the initial vertex of a given edge and what is the terminal vertex of the given edge. So as concerned for the external edges, we will always assume that they are oriented or outwards. This means the orientation is from the edge to the outwards, outside. Okay.
External edge is infinite or?
Infinite. This will be now associated with infinite intervals. So now actually we introduce the metric structure on this graph. This means any edge will be associated either with one comma or with one bounded interval, having the length AG. AG is positive. This is the case for internal edges, or any external edge will be associated with semi-infinite interval, 0 infinity. So what we get, we will call the metric graph. So, okay. And I would like to mention at this point, this orientation which we hasn't introduced right now, this is a kind of local parameterization, no more. If you don't like a specific parameterization, we can change it and can choose another. So the object slice Laplace operator defined on this graph will not depend on the orientation. It's a kind of parameterization. So now we are going to define operators. So we need to find a Hilbert space structure on this metric graph. And as an underlying Hilbert space H, we set simply the direct sum of L2s on all intervals our graph. That's a simply direct sum. It can be decomposed in the external part and internal part. The next step, so this is what are elements. What's the elements of H? It's a kind of vector function, which is numbered with the edges. And any component is a square integrable function on the corresponding edge. So now we introduce some kind of boundary value operators. So given a nice function on the graph, say Sobolev function on the graph G, we will define psi underlined. So the function has a name psi underlined. This is simply a vector with a dimension 2 times number of internal edges plus number of external edges. It consists, the first line, so we calculate all boundary values of the function from the external edges. The next step, we calculate all boundary values of the function from internal edges, which belong to initial point of the corresponding edge. So we calculate, first of all, according to our orientation, first of all, the values of the initial points. And then, actually, we will calculate the values of the function on the terminal points. So it's according to our orientation. First the beginning and then the end. So then we get this vector. So the notation K is introduced simply for compactness of presentation. It's simply a finite dimensional complex linear space. So we will do the same with derivatives of this function. In any case, boundary values. In the sense of boundary values, it's well defined. And by the derivatives at the terminal edges of the graph, we will put minus. So it's simply convenient for partial differentiation, simply notational convenience. Okay, psi bracketed. It's a vector consisting of psi underlined prime. So the space of boundary values is a space, is a direct sum of 2 copies of K. So derivatives and so the function, the boundary values of the function and boundary values of derivatives, they are put together. And now, so we introduce the Laplace operator given simply by second derivative of any edge of the operator with boundary values psi bracketed 0. So we put everywhere on any edge the boundary conditions. The value of the function has to be 0, and the value of the derivative has to be 0. So what we get, this is a symmetric, closed, densely defined operator. In any case, it's not self-adjoint. And the question which we deal in further, what's about self-adjoint realization of this operator? What's about self-adjoint extension of this operator? So actually what we have to do is the following. So we have a problem from the extension theory. Symmetric operator has to be extended. We can express all self-adjoint extension of the underlying operator. We can parameterize these extensions by unitary group. So the theorem of von Neumann. There is slightly another way to do this, and what we are going to do is the following. Actually, we start with a simple observation. It's stated here as a theorem, but it is much more simple as a theorem. Actually, it's a direct rephrasing of the definition what the self-adjoint operator is. So we look for the following thing. From the definition, from the domain of the sum extension delta, we calculate psi bracket. So we calculate the boundary values. And all these boundary values from all functions from the domain of delta, they form some linear space in our finite dimensional space of boundary values. So deficiency indices are finite. And now the observations consist in the fact that the operator delta is a self-adjoint extension of delta 0 precisely then if a Hermitian symplectic form defined in such a way vanishes on M and M has a maximal dimension. So M cannot be extended to larger space with the same property that omega vanishes on M. In other words, we have what is called maximal isotropic subspace, and one can also call this subspace complex Lagrangian plane. The only difference from standard Lagrangian language is the fact that we have here a complex structure. It's by interchanging of arguments of this form, we get the sign minus, but this is not the L, this is not all. We have also a complex conjugation. This is the difference to the case of, to the standard real Lagrangian case. Okay, if M is found, is given, then we will simply denote the delta of M for corresponding self-adjoint extension. Next step, that's just an observation. So we know that in the real symplectic theory, that orthogonal complement of Lagrangian plane is again a Lagrangian plane. The same holds with the same proof actually, that if M is, so a subspace M is maximal isotropic, if and only if it's orthogonal complement in the sense of usual Euclidean scalar product, also maximal isotropic. So this means we have a duality transformation which for any M prescribes its orthogonal component. If delta of M is self-adjoint, this means delta of M perpendicular is also self-adjoint. And so it's easy to verify this duality transformation since a Laplace operator with Dirichlet boundary conditions to Laplace operator with Neumann boundary conditions, and vice versa. So, in principle, the problem is solved. We wanted to describe all self-adjoint extensions of symmetric Laplace operator delta naught. So it's done. The question is the parameterization with the help of maximal isotropic subspaces is rather inconvenient. We don't know precisely how they look and so on. Perhaps there is a possibility to do this in a more simple manner. And there is one such possibility. First of all, this is a simple thing which is quite easy to verify. Subspace M is maximal isotropic if and only if there are two matrices, finite dimensional maps, such that AB, so it's a block matrix notation, has a maximal rank, and A by B star conjugate, Hermitian conjugate, is self-adjoint. Then the corresponding subspace is maximal isotropic, and vice versa. Any maximal isotropic subspace can be parameterized in such a way. What is the convenience of this transformation, of this parameterization? Simply the following: with the help of A and B, with the help of pair A and B, we directly describe the boundary conditions which we pose at vertices of our graph. This parameterization actually is ambiguous in the sense if A and B simultaneously will be multiplied with some invertible map T, then we will get the same maximal isotropic subspace. So, actually this is a simple corollary of just presented construction. So we have the following. The Laplace operator delta AB, so this is a self-adjoint extension of delta 0, is self-adjoint if and only if A and B has maximal rank and AB star is self-adjoint. And there is another possibility to describe all these operators. Let's look for the following construction. Actually, it is well defined for all cases different from 0. And the operator delta AB is self-adjoint if and only if S is unitary for some and hence for all k larger than 0. So just a short comment to the last sentence. If the S is unitary for some k0, then from this almost obvious identity, it's easy to see that S of k is unitary for all k's different from 0. So this slide shows this property. And now a few remarks. Actually, any unitary S defines boundary conditions for the some self-adjoint operator delta AB. This is a transformation which one has to use. Simply calculate A and B from S. Then the next one. What happens under the duality transformation with A, B, and S? So the first one is quite easy to verify. We should interchange the order of these two matrices A and B and put minus in front of B. And the second one, if we describe our boundary conditions in terms of S, then under the duality transformation, S will be sent to minus S. Also quite easy to verify. So what is just a remark about the meaning of S? So first of all, one can say, okay, we know that all boundary conditions has to be parameterized by unitary operators of corresponding dimension. This is what the theorem of von Neumann told us. And in any case, it's not a von Neumann parameterization of self-adjoint extensions, but this parameterization has the same dimension in any case. And another important feature of S. S actually can be interpreted as a scattering matrix. In which way? So we have a graph with external and internal edges. Let's cut all internal edges and let's replace any internal edge with two external edges. Two lines. This means what we get is a completely disjoint graph consisting of vertices attached to a number of external edges. And finally, S is actually the scattering matrix on this totally disjoint graph.
I don't quite understand. Then
Yes?
A and B should disappear if you did this.
A and B should disappear if I cut the graph.
Yeah.
Why?
So what happens?
Once more, I have perhaps.
So you cut the edges and what?
I cut.
A and B.
Just a moment.
A union of star graphs.
It's union of stars, right?
So I have this one. This
Oh,
is
you
my
keep-
graph,
You
okay?
keep the same. Okay.
Yes, I cut it. The dimension is as before, because the dimension is 2 times number of
Yeah,
internal
and-
edges. So this is okay. And so another important thing. So it's a slide full with description of the resolvent, I would stress on this slide only one thing. You don't need to read it so completely. If we would like to compute the resolvent of our self-adjoint operator, so this is the equation which gives it, and against it contains S, so it can be expressed in terms of S. So R0, this is so to say free resolvent given by usual free resolvent on the line, on the whole line. It's here. Okay, so now we consider some specific parameterization in terms of matrices A and B, and we choose A and B in the following way. Let A be an orthogonal projection. So possibly 0 or possibly 1, doesn't matter. So let L be some self-adjoint operator, self-adjoint matrix, with the property that it annihilates the complementary subspace to the range of the projection P. And now we said A is the sum of P orthogonal plus L, B is simply the projection. So, first question. Do these matrices A and B define a self-adjoint operator? The answer is yes. How to check it? So, let's calculate A multiplied by B star. This is precisely L. It's self-adjoint. And let's look for the rank of the pair A-B. It's maximal. Okay, this means that the corresponding subspace of A and B is maximal isotropic, and this means that the corresponding Laplace operator is self-adjoint. And the next question. So, do we get on this way all maximal extensions, all self-adjoint extensions? The answer is yes. So, it's quite easy to see. So, let's start with unitary, some given unitary as 0. It corresponds to, in any case, it corresponds to a self-adjoint operator. If S0 has an eigenvalue -1, let's split off this subspace. And on the rest, on the remainder, on the orthogonal complement of this subspace, we can consider the Kelly transform of the rest. So in any case, this transform is self-adjoint. Okay, let L be continuation, extension of L trivially by 0 on the whole of K. And now let's calculate the matrix SKAB by K equals 1, as we did it before. It gives precisely S0. So we get actually all self-adjoint extensions of delta 0 by means of this parameterization. So this is a alternative way of description proposed by Peter Kuchmet. So, okay, this is once more the same the statement once more explicitly. So we have for any maximal isotropic subspace, there are unique projection and some self-adjoint operator L, such that we can parameterize M by these two objects. So the next question, what happens with L under the duality transformation? So if we transform M to M orthogonal, what is the corresponding transformation for L? So the answer, L will get a minus sign. How to see it? So the simplest way, probably. So we know that M orthogonal is M of minus BA. So because the duality transformation sends AB to minus BA. This is what we know. This means that the duality transformation sends A by B star to minus BA star. And this is the same by the self-adjointness of AB star as minus AB star. Okay? So now let's put A is taken from the Kuchman parameterization, B is taken from the Kuchman parameterization, and calculate. It's the operator L. And the second one is operator minus L. This means the duality transformation changed the sign of the operator L. So then, quite important class of boundary conditions which are considered. So up to now, they were supposed to be quite general. There is an important class which can be characterized as local boundary conditions. So this means that the corresponding matrix S can be decomposed into an orthogonal sum of blocks Sk, M, V, such that any block belongs to a particular vertex V. If there is some decomposition, then we may state that the boundary, by definition, that the boundary conditions are local. And more intuitively, one can understand in the following way. So if we look for the boundary values at an arbitrary edge here, so the boundary conditions couple the boundary values of the function and its derivative only at this specific edge and not with the next edge. Then they are local. Obviously, this is the same as decomposition of the unitary matrix S. So, okay. So now let's turn to the next question, the number of negative eigenvalues. And first of all, let's consider the star graph. This is not the star graph as has been considered in the talk by Gregory, because these lines, these blue lines, are infinite. This is the difference. So we have actually a non-compact graph in this sense. And we ask the question, what is the number of negative eigenvalues on this simple graph? So, and the answer, the number of negative eigenvalues is precisely the number of positive eigenvalues of the operator A, B star. Actually, one could ask, just a moment, A and B describe the boundary condition, describes the operator in non-unique way. What happens if I replace A and B by different A prime, B prime, which define the same maximal isotropic subspace? So the answer is actually, if we remember, if we recall the Sylvester inertial law, the number of positive, the number of negative, and number of zero eigenvalues will not be changed under the similarity transformation. At multiplication by some non-singular matrix T from the left, this is actually the similarity transformation. In particular, from this observation, it follows that A, B star, and L has the same numbers of positive eigenvalues. The same is true, naturally, for number of negative eigenvalues and for number of zero eigenvalues. Okay. So, okay, quite short proof how to see it. So, if we make an ansatz, we are looking for eigenfunctions on this simple star graph. And we choose an ansatz of this form. So what we see immediately that the vector chi, this component chi j, has to solve this equation, this sum k positive. Okay, this means we have to count the number of positive number of positive zeros of the determinant of this matrix. So let's do it, and for the calculation, by the transformation T, we pass to the Kuchman parameterization. So we take from A and B, we construct the corresponding projection and corresponding operator L. So we are in the final dimensional case. This means that determinant of T can be factorized. What we get is this construction. And let's write down this construction in block matrix form with respect to orthogonal decomposition P plus P orthogonal. It is this form. So fine. This is a block diagonal matrix, and we can directly calculate this determinant. It gives determinant of L minus K. So actually we are done. L has, the number of zeros of this equation is precisely the number of positive eigenvalues of the matrix L. So let's go down further. What happens if we replace now our star graph with more general graph? Quite arbitrary graph. So actually in this case one can prove the inequality. There is no equality. And the inequality says that the number of negative eigenvalues of delta, of the Laplace operator, is not bigger than the number of positive eigenvalues of R by B star. So it's the upper bound. So I'm not going to prove this second statement. We can easily show a little bit weaker assertion, and namely, let's assume for a moment that the matrix A B star is non-positive. There are no positive eigenvalues at all. Then, so what we have to expect from the last inequality, the operator is positive. There are no negative eigenvalues at all. This is quite easy to see. So first of all, so let's compute the quadratic form of minus delta. It's a simple integration by parts. C bracket, as before, is a vector consisting of boundary values of the function and boundary values of its derivative. And Q is a asymmetric matrix with 0, 1, 0, 0. It's a block matrix notation with respect to this decomposition. And further do the following. So let's compute the orthogonal projection onto the maximal isotropic subspace M, parameterized by the matrices A and B. It's easy to see. This gives this result. So it's easy to see that this is an orthogonal projection, and it's straightforward to verify that its range is the same as a subspace M. Okay. If we have it, then in any case we know that Pm applied to the boundary value of psi, it's a function from the domain of our operator, gives the same psi. So psi lies, bracketed psi lies in the range of the projection Pm. Okay, let's use this information. This means we may put Pm 2 times here in the scalar product. And now let's start with simple calculations. This means we plug in the explicit expression for the Pm directly in this quadratic form, and we'll get this result. So now, what we have assumed? We have assumed that A multiplied by B star is negative. This was the assumption. It was negative, right? Okay. Now, in front of this expression, we have minus. And to the left and to the right, you see the same operator but conjugated. This means this is positive. This is not negative. So now, putting all together, so the previous calculation on the quadratic form, we arrive at the conclusion that this form is always non-negative. So there is no negative spectrum.
I'm sorry, I don't understand.
Yes?
It seems to me that I wrote down quadratic form in the form where this operator L is present, and you don't need any calculation whatsoever. Under this condition, you just look at quadratic form, both terms are non-negative.
Yes, Peter, you're completely right. We have already showed that B star is similar to L. This means the number of negative eigenvalues corresponding to the number of positive eigenvalues is the same. And this, what is written in your paper can be applied to this case. I thought this is a more direct, more simple argument, that's all. In any case,
I just thought that there was no argument needed. So you just look at quadratic
if,
form.
right, Peter, if you use your presentation for the quadratic form, then we are done. That's right. I wanted so to omit your calculation,
Okay.
yes, and to do this by, so let's say, by foot. By
I
foot.
just thought that there was some problem. Okay.
Okay. So, if we speak about non-negative Laplace operators, then it will be worth to mention a special class of positive operators, and this class is described here. The following conditions are equivalent. So we assume that M is maximal isotropic subspace, parameterized by some A and B. And now the following conditions are equivalent. First of all, S is K independent. S is self-adjoint for some K. S squared is 1. Actually, S has to be unitary. If it is self-adjoint, then necessarily S squared has to be 1. And A multiplied by B star is 0. And if you use the Kuchman parameterization, this means that the operator L is identically 0. It's the same. Okay. And if S is K independent, then naturally S under the duality transformation, so we get again an S independent and K independent S describing this situation. Just a couple of examples. So naturally, Dirichlet and Neumann boundary conditions. At any edge of the graph, we put Dirichlet and Neumann boundary conditions. What we get, simple calculation. It's -1, this is a scattering matrix for the Dirichlet boundary conditions, that's all. It's -1, you know that. For the Neumann, we will get 1. That's not unexpectable. The standard boundary conditions. These are the boundary conditions which are called Kirchhoff, Neumann, and so on. I prefer this name, the standard. So just to remember, this is a direct description of these boundary conditions. If we look locally at some h, then we have the following. So first of all, Cj of 0, this has to be this point 0, has to be the same for all edges j. And the sum of normal derivatives of psi j, say outwards, j is 0. And alternatively, we can describe these boundary conditions. We can describe these boundary conditions by the scattering matrix. This is a form dec. V denotes the degree of the vertex V, the number of edges emanating from this vertex. And if we look for the dual boundary conditions, then we get something which may be called co-standard boundary conditions. This means the role of the function and its derivative has to be interchanged. So this is a matrix. If you take some of these boundary conditions, in particular standard boundary conditions, and look for magnetic perturbations of Laplace operator, so in which sense? So we replace a Laplace operator by first derivative plus vector magnetic potential on any h. And then actually any of this transformation is reduced to the case of multiplication of the matrix S with an unitary matrix U, which has to be diagonal with respect to the vertex basis, and U depends on the magnetic flux through loops on the graph. So if there are no loops on the graph, then there is no magnetic perturbation. Okay, so among these boundary conditions, standard and Dirichlet boundary conditions are the only boundary conditions which correspond to a continuous function. at the vertices, and all other has discontinuity, especially if you look for magnetic perturbations, then we necessarily arrive to discontinuous functions, the functions which has a discontinuities at the vertices. And perhaps just one generalization of this result. If we look for the case of non-self-adjoint operators, what we ask, we are looking for the boundary conditions which correspond to maximal operative operators. These are the operators which has non-negative quadratic forms. They are no longer self-adjoint. They need not to be self-adjoint. Then we can describe this generalization as follows. So the real part of the A, B star has to be non-positive. The matrix S calculated for imaginary argument has to be contractive. Then we get all maximal accretive extensions. Okay, quite shortly, there is another statement for maximal dissipative extension, so I will skip it. Next question, so lower bounds on the spectrum. So if we look for the star graph again, then the situation is quite simple. So let's calculate the operator L. Let's calculate the maximal positive eigenvalue of this operator. And let's take it squared. That's all. This is the lowest eigenvalue of the Laplace operator on this simple graph. What happens if we look for general graphs? So this is a result by Peter Kuchland. The lower bound for the eigenvalue, for the eigenvalues on arbitrary graphs, arbitrary finite graphs. And what I would like to discuss is the following thing. So in this bound, we see this sum. So the number of external edges plus 2 times the number of internal edges. If we look by fixed L, let's say, we look for a large graph, then the right-hand side of this inequality will be very, very small. It goes to minus infinity. So this looks not quite satisfactory, and what I'm going to discuss is a possible improvement of this inequality. This is a corresponding result. So we consider the graph with internal edges. Otherwise, the problem is trivial. And this is a statement. The lower bound for the spectrum of the Laplace operator is some function, will be described right now, SA, of the norm of L plus squared. L plus is the positive part of the operator L. And the function S is defined as a unique non-negative solution of this equation. The number A is the smallest length of the internal edges. So some properties. First of all, if the argument of this function is 0, then this function is also 0. This is reasonable. If L plus is 0, then then the spectrum of the operator has to be positive. Okay. The first thing, if t goes to infinity, then the function will be linear. This is presented here. And the next property, let's take t fixed and consider the case a goes to 0. So this means, for instance, we take a fixed graph with a given geometry, and we will start to play with lengths of this, of the edges of this graph. We'll make them smaller. So this means the number a will be smaller. What we see that the function SA has a singularity of type of square root if a goes to 0. So the first question, let's discuss this inequality, this bound qualitatively. Is it reasonable to see this behavior? So the answer actually is yes. So this is a simple example. So let's take a line 0 to infinity and put somewhere a finite number of edges. in any case, we can interpret this construction as a graph. At any point, 1 over k, 1, 2, 3, 1 fourth, 1/5, and so on, we put delta interaction, the negative delta interaction. And we consider actually a finite number of these edges. So this is a graph, this is a linear graph, which is non-compact, but in any case, this object is in our class, in the considered class of graphs. Take some number kappa and consider the boundary conditions of this type at the point 0. So now we can define the Laplace operator on this graph. The question, how behaves the lower edge of the spectrum if we increase the number of edges? Increasing the number of edges will mean the diminution of the number A, because the number of two successive, the distance between two successive edges will be smaller. So take a test function, calculate the quadratic form, yields this result. And it is easy to see that this finite sum for n to infinity diverges. So this divergence means that the lower edge of the spectrum goes to minus infinity. So actually one may see that this behavior 1 over a square root is completely correct because the sum diverges as n to n squared. And 1 over n squared is precisely the distance between two successive edges. So this behavior is in any case correct. Okay, so quite short the proof, how to prove this inequality. So first of all, so let kappa naught, a positive number, be the biggest solution of the equation a minus kappa b equals 0. So actually, as is already mentioned, this is the biggest positive eigenvalue of the operator L. It's here. Now, let's estimate the matrix S. So put the operator L in the definition of S, we get this one. And if kappa is a little bigger as kappa naught, then we can actually not only estimate the norm, but also calculate the norm. This is this result. And this number is larger than 1, obviously. Okay, next step. So the number minus kappa plus squared, let it be the lowest eigenvalue of minus delta. So we are looking the bound for this number. And for instance, from resolvent equation, you can see that this number has to satisfy this algebraic equation. So the matrix T is given here. It's the matrix S, contains the whole information on the boundary conditions, and the matrix T contains the whole information on the edges of the graph. So this is a notation for diagonal matrices. Now, if kappa plus solves this equation, this means that in any case, the norm of S multiplied by T has to be larger than 1. So the spectral radius has to be at least 1. This means the norm has to be not smaller than 1. And then this means actually that this product has to be not smaller than 1. Okay? That's the last step. So now we may conclude kappa plus is not bigger than kappa 1. It's an infimum for all such values of kappa for which this product of two norms is smaller than 1. And since this inequality, okay, so the norm of S is already calculated, the norm of T can be calculated explicitly with the number A. A is the smallest edged length of the graph. So now, then we come to the conclusion that kappa 1 is not larger than the unique positive solution of the equation of this form. And this is the same as to say that kappa solves the equation for kappa is equals to the value of the function s at k0, at k naught. So we are done. Quite short discussion, nevertheless, once more. So let's look for the graph. And let's do the following. Let's move two edges, two vertices to each other. So let's make one particular edge of the graph shorter, 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 and shorter. What happens with the number a? The number a will go to 0. What happens with the lowest edge of the spectrum? Yeah, nothing special. It will be shifted to the bottom, but will remain finite. It's easy to see that. But in any case, our estimate has a difficulty in this limit. It goes to minus infinity. So this is not quite satisfactory naturally. Okay, the time is running out. What I'm going to discuss more, perhaps quite 2 minutes, about the simplicity of the lowest eigenvalue. So just a quite simple criterion. So if our boundary conditions are local, we look for this sum. This is a unit matrix plus S corresponding to the local part of the maximal isotropic subspace at the given vertex V. And now assume that this sum, this is the matrix, is component-wise positive. So all elements of this matrix are strictly positive numbers. Then we can say the following. The lowest eigenvalue of the Laplace operator is simple. So the proof actually is by using semigroups. Okay. So at this point, I will stop. Thank you very much for your attention.
Questions? Questions, comments?
Just a small remark or question relating to the statement that only Dirichlet and Kirchhoff boundary conditions give rise to continuous functions. You probably mean generalized Kirchhoff, because in this sum of the normal derivatives equal to 0, you could place sum of normal derivatives equals to a constant time the value of the function.
Within the class of energy independent, of K independent.
So these ones would lead to K dependent.
If you put here something,
Yeah?
let's say beta, you will get immediately.
No, I mean beta times.
Right. Beta times psi, let's psi k. We will get immediately the codependence.
Oh, you mean depend in the scattering matrix?
Right.
Any other questions?
What's on the slide 27?
It's it's a list of references. So very incomplete. Nothing special.
Any other questions? Is there none? Then let's thank the speaker again. I have an announcement that next week we do have 4 seminar talks, but you will